Okay, I'm going to talk about interest, simple and compounded. So, and we're talking about interest like you make on money if you put it in a savings account or something like that. So, simple interest. If I had a 5% interest per year, my simple interest would be if I put in $100, the next year I would get the $100 plus 5% of $100, which happens to be $5. The next year, I get my $100 plus 5% of the original $100, which is another $5, so I'd have $110. And if I have put in $100 after 3 years, I get another 5% of my original amount, which was $100, so I get another $5 or $115 would be in the account. That's simple interest. So the interest is always 5%, which of course is 0.05 in decimal, that times 100, and add that on each year, same amount. It's always the interest based on the original amount put in. Now, compounded interest, after you put the interest in after the year, then you get interest on this amount and not the original amount. So you're starting to get interest compounded, added to based on the interest that you've added to the account. So that would look like at year zero, if I had $100 in the bank, then after 1 year, I would do 5% of this, which would be 105, so nothing's changed. But in year two, it changes. Now I get 5% of this. So I would originally put $100 in, and then I can go times 0.05, and that's how much interest I get, and I add it to the $100. Now, I want to do this, and then I would take the 105 times 0.05, and I'm going to get $5.25 added. So now I'm going to have not 110 like before, I'll have 110 and 25 cents. Doesn't seem like much difference, and it's not really, but what happens is it grows. It makes a difference in a longer run. So the next time it'd be 110.25 times 0.05. And I'd have to add that to that. So I got 3 and then 115 and 76. Now, instead of doing this as a two-step process, multiplying by 0.5 and then adding it to the last number, we can do this a different way. To go from 100 to 105, we can start with 100, and then we want to multiply by 100%, which is 1 in decimal, plus the 0.05%. So I'm going to find 100% of $100 and 5% of $100 and add them together. So I'm going to do it in one step. And there's the 105. And since I use the answer feature of the calculator, I could just press enter again, and there's the 110.25, and there's the 115.7625, and there's 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, and I can work my way up pretty quickly that way. But in a formula, an exponential formula, the amount that I have after some time is the amount I started with, which in this case is $100, times 1 plus the interest rate, in decimal form. This is called the annual percentage rate, APR. So some books will just use R, some will do the APR. Divided by, well, right now we're not dividing by anything, to the number of years. And that would be the amount I have after T years. So I would do, if I wanted to find 3 years directly, I would type in 100, my starting amount, parenthesis, 1 plus 0.05, close parenthesis, to the third for 3 years. 1 plus APR T to the third. And I get my 115.7625. Okay? Now, this is compounded annually. Every year you get your interest. But some institutions will compound more than annually, give you your interest more often. Like maybe monthly. So then this would start off with 0 is $100. And then after 1 year, well, it's going to be a little tricky because you're going to get your interest each month. So we have to modify our formula. The amount we get after some time is going to be the starting amount times 1 plus the APR, the interest rate, divided by, you're not going to get the full 5% in 1 month. It takes a whole year. So you have to divide the interest rate, 0.5 or whatever it is, by the number of times you're going to get that interest in a year. So if we're going to get 5% for a full year, but get it every month, we have to take 1/12 of the interest rate is how much we would get in a month. And then we would take it to then we'd have to do this 12 times to get it for 1 year. And then for 2 years, we'd have to do 24 times. So 2 times 12 would be 24 to get through 2 years. And for 3 years, we'd have to do 3 times 12. So this would be the formula. So let's see how much that changes this. So if I started with $100, parenthesis, I get 100% of that back plus 5% in decimal divided by 12, close parenthesis, to the 12th. That would tell me how much I get after 1 year. And it was 105. Now I'm going to get a little bit more because I'm getting my interest on the interest, and it's 105 and 12 cents approximately. Now, let's do it for the full 3 years. So I'll bring my last answer back and take it to, I need to put this in parentheses on the older calculator. I need to go parentheses 12 times 3, or make it 36 up there. And in 3 years, I'd have 116 and 15 cents, 14.722 dollars. So now you see I've went from 115 in simple interest, compounded annually, I went to 115 and 76 cents, and monthly I'm at 116.15 cents. So what if we did it daily? Well, then instead of 12 here, we have to split our interest rate up 365 times in a year, but then we have to do this 365 times per year. So what you're getting is a formula in general. The amount of money after some time t is equal to the starting amount times 1 plus the APR over, divide that by how many times you're compounding it in a year, how many times you're going to get that interest in a year. Daily, this is 365. Monthly, this is 12. And we're going to take that to the NT, number of times you did it in a year times the number of years to get it. So let's figure out how much that changes 1 year. So 100 parenthesis 1 plus 0.05. Now, if I'm getting a different interest rate, I'd have to change that number. Divided by daily is 365, close parenthesis, 2 parenthesis 365, close parenthesis. That would be for 1 year. And now I've got 105.13 cents, just barely rounding up to 3. Not showing up much different there. What happens is it shows up a significant difference in the long run. 3 years is not a long run, but let's see what it would be in 3 years. So I'm going to bring this back, and I'm going to take my 365 times 3 for 3 years. And now I'm at 116.18. So a little bit better than monthly. 1.8, I'll just put on the 2.2 just to keep track of what's going on here. Now, what if I did it every second? Well, then I'd have to put down here how many seconds there are in a year and how many seconds there are in a year. So that would look like the amount after, let's say we'll do it for 3 years, would be the amount we start with times 100% of that we keep, plus the percentage rate, which we're going with 0.05, and the number of seconds in the year would be 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds every minute. And then I have to take it to the power. This number, 365 times 24 times 60 times 60 times the number of years. This much each year for 3 years. So now let's see how much more I get. Not going to be very much more, but let's see. So 100 parenthesis 1 plus 0.05 divided by, now I've got a complicated denominator, so I got to put it in parentheses. 365 times 24 times 60 times 60. And that's closed. I got to close this with this parenthesis. I put parentheses here. So now I need another parenthesis, closing, to the, now I got to open my new exponent parenthesis, 365 times 24 times 60 times 60. Did I get it all in right? Yep. Times 3. So that's for 3 years. And it's 116.1835. So I got a fraction of a penny more. Okay? Well, not very often they do it per second. You might get daily someplace, but then they often go to just compounded continuously. And that is a different formula. That's the amount you have after some time. is the amount you start with, e to the APR, the interest rate, in decimal times the number of years, t. E is Euler's number. He's a Swiss gentleman who was working with this stuff, and he discovered this E. So let's see how this would work for 3 years. So E can be found on the calculator. E to the x is there, and E is right there above the divide sign on this calculator. And you'll find it on most calculators. So I'd be doing 100 e to the interest rate at 0.05 times 3 for 3 years. So this is compounding it more frequently than every second, like every microsecond. So it should be slightly higher than this number. Let's see what happens. Oh, it came out slightly lower for some reason. Not supposed to be. But anyway, this is compounded continuously. You can see it's slightly 3.183. It's supposed to be slightly higher. I don't know why that one got me confused. I'll have to think about that one. But anyway, yeah. Okay. So if you're getting compounding very, very frequently, it's easier to use the compounded continuously formula. Okay? Now, related to this, by the way, E, Euler's number, in case you want to know what it is, second E, it's 2.7, 1828, 1828, 4590, 45, blah, blah, blah. If you walk the halls of Samuelson Hall upstairs, you'll see a board listing it to thousands of places. Okay. So this is a growth model because E is 2.7. It's bigger than 1. Now, if there was a negative exponent, it would be a decay model. But since this is a positive 0.05t, that's a positive exponent, it would be a growth model, and we could graph it. And what's special about E? If I were to graph it, let me just do it on here. Let's just do e to the x. And if I go, I'll just graph. And e to the 0 is 1. E to the 1 is 2.71828, whatever. And e to the 2 would be that number squared. What is special about this graph and what is special about E? I'm going to zoom out. And that's not very good. Let's go zoom 6. If you pick a place on the curve like at 2 and find the y value, second table, let's put in 2. The y value is this, 7.3891. But on the graph, the height is 7.3891 or whatever that number was. It's also the slope of the graph. This is the only curve in mathematics, in science, where the slope of the graph is equal to its y value. Now you could type in 2 to the x, and it's close to the same shape, but not growing quite as fast because the base is not as big. Or you can type in y equals 3 to the x, and this one will grow faster. So on this one, the height will be less than the steepness. On this one, the height will be more than the steepness. And the only graph where the height of the curve is also equal to the steepness of the curve at that value is the exponential with base e. That is why e was figured out in the first place and became an important number. And the reason that is important is if you have a few people in a town, then how fast the community is growing will be based on how many people are there. If you're in a big city where there's thousands of people, then the rate of growth of that city will be steeper. So the rate of growth of a community depends on how many people are in the community. Just like the height of the curve also predicts how fast it's changing. And E is a good model of a curve where the height also reflects how fast it's changing, the slope. And so growth models or decay models, if you have radioactive material, and that is radioactive materials like a couple of molecules that are a couple of one big atom that if it split apart would make two more stable parts. And it's not very stable when they're connected. And so when it splits, it emits radiation. That's why it's called a radioactive particle. And that radiation can be harmful to people. But when it splits, then it becomes stable things and not radioactive. Well, if you got a bunch of these molecules, after a certain amount of time called the half-life, half of it, now it would be half of the molecules all spread out all through here, but basically you could say this half would split and be stable. Then after that same amount of time, if the half-life was 7 days, let's say, then in another 7 days, half of what was still radioactive would be radioactive and half of it would have stabilized. And then after another 7 days, half of that, and another 7 days, half of that, and half of that, and half of that. That's how half-life works. So the amount of radioactive material to start with times 1/2 for every half-life. Every half-life time, if it was 1 half-life, 7 days down the road, you put 1, and if it was 14 days, you put 2 for the half-life, and that will tell you how much is left. That's radioactive decay. And that's a model that looks like this. Now you can also do it with e to the something, and you can do growth models with e. All that means is you're going to change, instead of doing 1/2 to some number that takes care of the 7 days, you just write e to some constant times t. And so instead of having a base of 1/2, you have a base of 2.17 to some k, and that gives you the correct model for it. So we're going to get into that a little bit, but that's kind of what's going on here. It's all related to this, a base to an exponent, and if this base is bigger than 1, like these were, 1 plus 0.05 over, it's going to be a growth model, and our savings account will grow. If it's some kind of account where we're losing money out of it every year, it's losing 5%. For instance, suppose I have $1,000 invested in stocks or something like that, and things are going bad poorly, and I'm losing 2% per year. Well, then I'd be taking it times 1 plus a negative 0.02. And then if this is compounded monthly, or let's do daily, 365 to the 365t. And this will be less than 1, so it'll be decay model. If it was doing it annually, if we had something where we were losing 2% per year, another way to look at that is we would have 100% minus 2% loss, so we'd be keeping 98%. And so if we were doing it annually, we'd want to take the amount we started with times 0.98, and that would mean we're decreasing. So if the base is less than 1, we're decreasing. If the base is 0.98, we're losing 2% per year. If the base is 1.02, we're gaining 2% per year. Okay? Hopefully that'll help.